Hey, this is Andrew McLaren here. Today we're going to be talking about why average atomic masses will come out as decimals, as well as why the mass of isotopes come out as decimals. I'm making this because I Googled this question and there was no good resource really explaining this. There's some people who said things that were kind of right, like they were like half true, but not all the way true. So I wanted to help you understand this. Basically, we're going to talk a little bit about protons, neutrons, and electrons. Then we'll define AMUs and really look at this decimal stuff with some math worked out. That's the overall plan. Okay. So there's a few things that we have to clarify about protons, neutrons, and electrons, and help you just kind of see that in a model, and then that will help a lot when we're talking about them later on. So if we look at this simulation, the build an atom simulation, you can have protons and electrons. And if I add on another proton, I have helium here. And you can kind of see how this goes with the periodic table. I want to have this be neutrally charged. That's why I'm putting electrons on there. Lithium is actually going to have some neutrons on there, though. And you can see that this is lithium that has 4 neutrons on there. And so it's got a mass number of 7, and it's neutrally charged there. So this is the general idea when we're talking about protons, neutrons, and electrons. You can have lithium have 4 of these neutrons, and then you can also have it have 3. Those are different isotopes. So we can talk about other things, like if I have beryllium, this is neutrally charged beryllium. It's got the same number of protons, neutrons, and electrons. And it's important to know that these are always whole numbers. The number of protons, neutrons, and electrons, they're whole numbers inside of an atom. And then we're going to be thinking about the number of those things for different isotopes a lot of the time. So like beryllium, there's slightly different versions of beryllium that look like this. Like maybe it's got a lot more neutrons on there. Typically, the more common isotopes are the ones that have similar numbers between these three, is what I've noticed at least. But it's not always exactly that, and we'll talk more a little bit about why it's not exactly that. Okay. That's my quick overview of how these things are related: isotopes, protons, neutrons, and electrons. Okay. Actually, I also want to show you the symbols and how that changes. Just really quick. So if we have this hydrogen atom by itself, you can also have different isotopes of that hydrogen atom. That changes how much they weigh, because neutrons weigh stuff, right? But still hydrogen. If I add in this, then we're going to have like a different element here. We've got helium, and it's going to have possibly 2 neutrons, possibly 3. That also is going to be a fairly common isotope. And that helps you kind of see how these numbers are related when we're talking about these things. And then sometimes they'll give charge as well up here. So if we had an extra electron, that would be the charge there. Okay. All right. So what is an AMU? It's kind of complicated. It was originally defined as the mass of 1 proton, but then as we learned more about chemistry, we realized that that doesn't really work very well. Uh, I'll go a little bit more into that with the decimal part. But for now, all you need to know is that an AMU is defined as 1/12 of a carbon 12 atom, which is basically 1 proton. So if we looked at, like this is a hydrogen atom and it's only got 1 proton. So this has an atomic mass of about 1. It's a little bit different than 1, but it's about, we can say 1. So if we wanted carbon, we're going to need 6 protons. And then we're going to need 6 electrons, or 6 neutrons, I should say. And then we're also going to have 6 electrons. And when we do that, we get a neutral carbon atom here. And this is carbon 12. So you can see that because it has 6 protons and 6 neutrons, it's got a total weight of about 12. And for carbon 12, this is exactly 12 AMUs. It's the only thing that works out this neatly. because if you actually add on one more proton, it's actually not a whole number. It's a little bit different. So if I went to the interactive periodic table and I showed you the isotopes for carbon, carbon right here has a number of different isotopes. And you can see carbon 12 weighs exactly 12, but carbon 13 does not weigh exactly 13. It's a little bit different. It's got a decimal, and we'll talk more about that soon. Carbon 14 also has a decimal on it, even though you're adding in whole numbers. So let's take away one of these. So we're back at carbon 12. So this is like carbon 13, and then this is carbon 14. And so, yeah, here they're displaying them as whole numbers for the number of protons and neutrons that are here. But if you were to think about its actual weight, carbon 14, it's not quite exactly 14. It has to do with basically a loss of mass, and we'll talk more about that soon. But I want to talk briefly about where you're likely to see AMUs. So when we see something like this, this is an element. There are many isotopes here for this. So this is many isotopes being averaged. So like carbon 12, and I have a whole video going over like percent abundance of an isotope and how it contributes to the whole mass. But you can think about like 12, carbon 12 being the most common. And so its atomic mass is going to be about 12, but it'll be a little bit more because it's getting some additional weight from carbon 13 and 14. But be careful because you also will sometimes see like whole numbers displayed on these things. And if they're talking about some whole numbers, it's either the number of protons, because for an element, it's got a whole number, and an isotope, that's a whole number as well. If we're talking about the mass of these things, sometimes they'll talk about that of the isotopes and of the element as a whole. So this, you gotta be careful there. Also, they'll move these numbers around a little bit sometimes. And I wanted to briefly point out how this is a little bit different than if you have like carbon 12, you'd write out something like this. This right here is not the atomic mass. It's the protons plus the neutrons. It's just the number of these things, the number of protons and the number of neutrons. It should be close to that, but its actual weight oftentimes is a little bit different. So for most elements, it's not exactly 12. For carbon 12, it is actually exactly 12. But if we had like carbon 13, its AMU was like 13.003 something. Carbon 13, yeah, it's like 0.003. Yeah. So that's the idea of what an AMU is. It's basically 1/12 of a carbon 12 atom, which is pretty much the mass of a proton, but not exactly. And I'll explain more about why that is in the next bit, okay? So when you Google this question about why there's oftentimes decimals given for the AMUs of a certain element, there's a couple different answers. You'll oftentimes see people say, well, that's because you're averaging out different isotopes, which is partially true. But the isotopes aren't made of whole numbers. So you're not only just gonna get a decimal because you're averaging out things, but you're also averaging out things that have decimals. So it's important to keep in mind that most isotopes besides carbon 12 are not going to come out exactly as whole numbers. It carbon 12, I think it does weigh 12 exactly, but it's kind of weird. There's also something to keep in mind that an AMU is, some people will tell you that an AMU is like kind of between a neutron and a proton, and that's somewhat true, because you would think like, oh, I've got 6 protons and 6 neutrons. So if I add those two together, I get 12. I don't know what their exact values are, but if I divide by 12, I should get something that's in between those two values, right? Like if this was worth 10 and this was worth 12, and you add those both up, then and divided by 12, then you'd get an average of like 11, right? So, or if it was like 20 and 24, you'd get an average of 22 if you added those all up and then divided them. But that's not exactly true, because yes, protons and neutrons weigh different amounts, but an AMU isn't actually technically halfway between the two of them as well. And it has something to do with a loss of mass that occurs when protons and neutrons form a nucleus. That's the main idea here. And don't worry, I've got visuals to kind of show this. I'll get to that soon enough. I just wanted to talk about this bit, and then I'll refer back to it. The main thing, though, is that these things are going to be gaining or losing, like protons and neutrons, they gain or lose mass as they're forming or breaking apart from a nucleus. That's actually where nuclear power comes from, is this energy that's being used to hold the protons together. You can think about it like protons are a bunch of positive charges, so they don't really want to be next to each other. So there has to be some energy used to like kind of glue them together. And the nucleus actually loses some of its mass and turns that into energy that holds the stuff together. So if you actually weighed an individual proton, which we can do because protons freely float around all the time, if you actually weigh them out and compare them to what we've defined as an AMU, it weighs 1.007277 AMUs. And so if you also weigh out a neutron, you can see its weight, and the weight of an electron, you can see its weight. If you multiply those each by 6 and add them up together, you get 12.09, which is very strange. For carbon 12, as we've said before, it's defined as being 12 AMUs. But we seem to have a loss of mass here, because you would expect if you added 6 neutrons, 6 protons, and 6 electrons to get 12.09. In reality, it's actually 12. So there's this loss of mass that's occurred, and that loss of mass is basically energy or subatomic glue that's being used to hold all these things together. And if you were to actually separate them back out again, you would get that mass back. Like if you were to actually pull apart these protons and neutrons and electrons, you could actually get a total weight of 12.09 again, because now you've unglued, you can use that energy again and have it be mass. One thing to keep in mind is that this amount that this loses, the amount of matter that you're needing to use to bind this stuff together, is completely different for different elements. And so that's why when you have, let's say instead of carbon 12, you looked at, what is it, like chromium 48, right? So chromium 48 right here, you might think is going to weigh twice as much, but it doesn't, right? So it's like this carbon 12, or sorry, not carbon, I'm messing. I think what I wanted was actually magnesium 24. You might think that this is going to weigh like 24 AMUs. That would only be the case if the loss of energy was proportional, or like the nucleus was like requiring the same amount of mass per proton be turned into that glue. Because they're different, each element's a little bit different how much energy it's going to require or release depending on the proton coming in or leaving. these numbers are all over the place with the values that you actually get from this stuff. And I want to show you and just kind of play around with this. Like isotope 235, if we have like uranium, you can see how many protons and neutrons there are and see what mass you would expect. And if we look at uranium, so it's uranium right here, and it looks like it's not gonna, oh, here we go. It's displaying them now. So we've got all these different isotopes here of uranium. And if we want uranium 235, that guy right there, you can see that there's, well, because it's uranium, we know the number of protons was 92, and we have 235 as the protons plus neutrons. So the neutrons should be 235 minus 92. So you can do a little bit of math and see like, oh, there should be 146 of these neutrons, times that by the weight of neutrons. There's 95 protons, times that by that weight. And you can see that this should be weighing 239, let's just say, or 240. In reality, this thing weighs 235. So we're expecting, if there wasn't any loss of mass, this thing to weigh about 240, but it's weighing about 235. That's because some of that mass now has been converted into that glue that's holding this atom together. So this is needing like quite a bit of glue to hold all the stuff together. So you can think about the AMUs being different than what you would expect because there's glue. And so when we have carbon 12 and we're defining that as 12, we're trying to make something that's easy for us to measure. Carbon 12 is very common. It's very easy for us to determine how much that weighs. And so we can compare that 12, which we're like, okay, this has been clearly defined and easy for us to actually directly measure, because it's easier to work with carbon 12 than like neutrons and electrons and think about those masses. So that's kind of where it comes from. Okay. I did also want to show a couple more examples using the p-table isotopes. So if we look at like hydrogen 1, we've got different isotopes of hydrogen. If you look at just the normal, remember it's got like the atomic mass down here. And then we've got a couple different isotopes of hydrogen that are being combined here. So if we look at hydrogen 1, we can see its mass is 1.007825. And you can actually see that that's pretty much the amount of mass from one electron and one proton. If you were to add those two up together, you get this weight. There's not really any binding energy because it's just a proton by itself, so that's okay. But when we look at hydrogen 2, if we look there, we've got hydrogen 1 and hydrogen 2. Hydrogen 2 weighs not quite exactly 2 times that, but close, right? You might expect it to weigh, if you actually do the addition on those things and do the math, hydrogen 2 you might expect to be 2.016487 if you were to actually add in the proton, neutron, and electron. So there's a small amount of AMUs that's being converted into energy to hold this stuff together. It's not that much that's needed at this point, but you can imagine that if we get much larger stuff, it's going to need a lot more energy to hold the stuff together. So it's not just like, if you think about, this is like multiples of 8. Not like, it's not going by like 0.008, 0.016, 0.024. No, it's like increasing the amount of energy needed per time that we go up, right? So that's the main idea here. And then if we also go to the build an atom and just look back at that, we are looking at like hydrogen 1. which is just the proton and the electron by itself. So there's no real binding energy. But here there has to be that binding energy because they're attached to each other, right? And then we have our one electron out there, and so that's okay. So if we add all that up together, you can see that there actually is less mass in reality than what you would expect given the mass of the protons, neutrons, and electrons involved. That's why AMUs are not whole numbers. It's because when you make an atom, these things lose mass. And so we're just using a unit that's defined based off carbon-12 and how much mass it weighs. So I actually built a neat little tool here as well, where you can change the numbers here, and that changes the final mass that we're calculating here. And so this is basically what I was just talking about there. So we can have like hydrogen. So we can say that we're talking about hydrogen. This is like hydrogen 1, so it's just one hydrogen by itself. And then if this has got one neutron, this is hydrogen 2. And so you can see that in reality we have you can see right here that we have our hydrogen 2, and it's weighing a little bit less than what you would expect given its masses, because it should weigh that, and it weighs a little bit less. And then this should be weighing that much, but it weighs a little bit less when we're talking about the hydrogen 3 right here, right? And then hydrogen 4 is actually weighing this 4.02. And then, sorry, I keep on clicking on the wrong thing. That's what you would expect it to weigh, given the weights of the things that you're plugging in, but it actually weighs a little bit less in reality. We're talking about that hydrogen 4. Okay. All right. That's it. Thanks for joining me. I'll see you around. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about. And remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia. And if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.